Welcome to Deep Dive, the podcast where we explore amazing and sometimes mind-bending, twisting stuff. I'm your host, Ben, and today we're venturing into the intriguing world of quantum computing. You might have heard that quantum computers are the future, that they'll solve everything from climate change to financial crises overnight. But here's the twist. While quantum computing is incredibly powerful, it's not a one-size-fits-all solution. Think of it more as a specialized tool than a magic wand. So, what exactly is quantum computing, and why isn't it the ultimate fix-all some make it out to be? Stick around as we break it down in straightforward terms. To understand why quantum computing isn't the universal solution it's often touted to be, imagine it like a Formula One race car. It's an engineering marvel, fast, sophisticated, and designed for a specific purpose. But you wouldn't use it for a family road trip or to pick up groceries. Similarly, quantum computers are built to tackle very specific types of problems, especially those involving complex mathematical models. Quantum computers use qubits instead of traditional bits. Unlike bits that are either 0 or 1, qubits can exist in multiple states simultaneously thanks to a phenomenon called superposition. This allows quantum computers to process a vast number of possibilities at once. However, without a clear problem to solve, a well-defined mathematical model, all that computational power is like a race car revving its engine with nowhere to go. Think of a quantum computer as an explorer capable of traversing multiple paths in a maze at the same time. Without a map, it's just wandering aimlessly, even if it's covering a lot of ground. That's where mathematical models come into play. They act like a map, providing direction and purpose to the quantum computer's capabilities. Take quantum annealing as an example. It's a method where the quantum computer seeks the lowest energy state to solve optimization problems. Imagine trying to find the shortest route through a complex maze. The mathematical model, the maze's design, guides the quantum computer, while annealing helps it efficiently find the optimal path. Without this framework, the quantum computer wouldn't know where to start or what constitutes a solution. Another critical aspect is the difference between physical qubits and logical qubits. Physical qubits are sensitive and prone to errors due to environmental noise. To overcome this, multiple physical qubits are combined to form a logical qubit, which is more stable and reliable. It's akin to building a sturdy bridge by reinforcing it with multiple supports. However, creating logical qubits requires precise configurations and extensive error correction, making the process complex and resource-intensive. Quantum annealing excels at optimization problems, but it's not the only game in town. Classical computing uses techniques like gradient descent to find optimal solutions. Picture a hiker descending a mountain, always taking the steepest path downward to reach the valley. While gradient descent follows one path down, quantum annealing allows you to explore multiple paths simultaneously, increasing the chances of finding the global minimum rather than getting stuck in a local one. This is where artificial intelligence and machine learning come into the picture. AI can enhance quantum computing by helping to design and refine the mathematical models that guide quantum computations. If quantum computing is our Formula One car, AI is the pit crew and engineers optimizing every aspect of its performance. Machine learning algorithms can analyze vast datasets to identify patterns and variables that should be included in the quantum model. They can help configure quantum circuits more efficiently, reducing errors and improving overall performance. In some cases, generative AI can even propose new quantum algorithms or configurations that human engineers might not conceive on their own. So, is quantum computing a powerful tool? Absolutely. But it's not a standalone solution to all our problems. Its true potential is unlocked when combined with precise mathematical models and enhanced by AI technologies. It's a collaborative effort. Quantum computing provides the computational muscle, mathematical models offer direction, and AI adds intelligence and adaptability. Without this synergy, quantum computing is like having a state-of-the-art camera without a subject to photograph or a lens to focus. It's powerful but lacks purpose. As we continue to develop these technologies in tandem, we'll be better equipped to tackle some of the most complex challenges facing us today. Thanks for joining me on this deep dive into quantum computing. If you enjoyed this episode and want to explore more about the realities behind tech headlines, stay tuned for our next episode. Meanwhile, don't forget to subscribe and like, it helps us a ton. Until then, I'm Ben, and this has been a deep dive.